Thank you. Hi, everyone. So I will bring in a new point of view, which is the one of the DSO. So it will complete nicely what my colleagues just said. So I will illustrate my example with a project we realized last year. So I just gave a few key figures about Romand Energy. So we are a DSO, but we are also on other businesses. So we have thermal and electrical power generation, and last year we generated roughly half a terawatt of renewable energy in Switzerland. And we are the first electricity provider in French part of Switzerland with 250,000 clients. And for half of those clients, we have a smart meter which is installed. And we'll see that this information is important for the following of the discussion. So I will go briefly on this because it's kind of basic. But what is an electric load profile? So it's a measure we take with smart meter. Each 15 minutes, we will measure like the electricity consumed or produced during the last time period. And why do we need some synthetic load profile? So as my colleague said, like we have a bit of, we are in the middle of an energy transition, and our customer behavior is changing. Basically, for our grid planification team, it becomes more and more complicated to do their job because like we no more can rely on what we knew from before with the increase of PV panels, in fact, and also on the lower voltage part of the grid, we almost have no visibility. We are starting to have some now with the smart meters, but still they are not capturing the load curve. All of them are not capturing the load curve, and therefore we need some visibility there. And there is also another big constraint which comes from the NLPD, where basically load curve are considered as sensitive data, and therefore we should anonymize them where it's needed. There are also other needs for those synthetic curves. So the tariff teams, basically we have we have more and more like big peaks during a certain hour of the day, and there is a need to reduce those peaks. And one way to do that is to propose new tariffs so that the peaks are kind of reduced, because it will motivate our customer to consume at other moment of the day. So the main idea here of this project was to adding value to the smart meters by developing some synthetic load curves and then allocate a load curve to each kind of customer we have. So the first question we had to ask ourselves is, how do we cluster our customers? So for this, we did kind of simple approach about metadata clustering. So for each one of our 250,000 customers, we have 42 features at our disposal. So it can go from different categories. So it can be yearly consumption in kilowatt hour. It can be tariff. It can be the type of heating system. And we gather this information coming from two data sources. So SAP, which is our ERP, but also we are using some open data coming from the Swiss Confederation. And then, as I said, each customer will have a different set of data. So we are clustering those to have like a significant group representing them, to finally have one cluster and one synthetic load profile per cluster. So here, the main idea, we didn't use machine learning as a way to automatically associate a client to a cluster, but we use machine learning as an exploration tool for our business expert to tackle this problem under another perspective than the one they have on the previous knowledge on the business. So what we arrived is a kind of decision tree. So here it's a small part of our decision tree. It is on 3 levels. So the more deeper you go on the level, the more detail you have. If we take the first row, so we see that on level 1 we have individual individual houses. On level 2, we add information about the heating that our client has, and on the third level, we add the tariff. What we have to understand is that each one of these nodes is a different cluster, and in theory, the synthetic load curve beyond should be significantly different from one cluster to the other. For example, if you take an individual house with electric heating or an individual house with a gas heating, the electricity consumption won't look the same at all. And here, what we have is the final decision tree. So we have roughly 40 clusters. And also, you can say why we are always going on the third level, why we are not using every time the third level. It's because we don't have, for the moment, enough data. And sometimes, for some clusters, like we didn't add enough data to generate a good synthetic load curve. So it makes sense to go to the upper level. So it means level 2. So, but how do we generate our synthetic load profile once we have these clusters? So on the grid, on the low voltage part of the network, there are different actors. So first we decided to look at the consumers, because first they are the biggest part of our clients, but also because like they are the most simple to start with. So here what we did was not rocket science at all. Initially, we wanted to do some GAN or stuff like that, but in the end, we will see that we had a really simple stuff. So we had a simple statistical model where basically for each cluster we have some curve associated behind, and basically what we take is that for each timestamp we are doing an average of the value, and then we are doing so for all the years. And then in the end, we have a single time series that we normalize so that it sums up to 1. And then in the grid planification tool we have, basically what we do is that we multiply this synthetic load curve by the annual consumption of the client so that it scales up to something meaningful. And then when we are doing our simulation, we also add some kind of randomness, because otherwise, like our clients will in the same cluster will have a peak at the same moment, because it comes from only one curve, and therefore like we'll have some artificial peak which are not useful for us. So this is a kind of results we obtain. So on the green curve, what you can see is the tree measurement we have on the low voltage part of a transformer, and the brown curve is the one we generated by our synthetic profile. So basically what we add is that for this portion of the grid, we run a load flow using 125 synthetic curves, and basically we obtain these results where we see that the performance are kind of satisfying, because we see that, for example, the midday peak is almost perfect, but the one at 7 p.m. we are a bit above, but still the performance are interesting. Especially if we look at the red curve, which were obtained with some old profile we had in house. So as I said, we have the consumer, but we also have some self-consumer. So basically, it's the individual house and the property, the owner decide to put some PV panels on the top of it, and therefore they are kind of using the PV generation to consume on this part. And what we have here, our objective is to reconstruct the true consumption of the self-consumer. But the problem is that it's data we are not collecting. Smart meters are not measuring the true consumption. It's measuring something else. But true consumption can be determined with this kind of formula, which is basically the electricity drawn from the grid plus the production we have on the roof minus the electricity which is reinjected into the grid. So basically the last part is the self-consumption. And what we are measuring with smart meter data is the both electricity reinjected into the grid and the one which is drawn from the grid. but there is still a problem because production, again, we are not measuring it. So what we've done is that we need to generate a synthetic load profile for production. So basically what we did is exactly the same than what we did for consumption, where basically we took all the curve we have of true production, and we normalize them on the power of the installation. But like this, at least we have a good approximation of the production. And then there is this $1 million question, which is there a difference between the consumption behavior of self-consumer compared to consumer? And what we observed here, the answer seems yes, because the blue curve is a curve where we are, basically it's the curve we will see on the book, because we have a bigger peak around 7 p.m. and the smaller peak around midday. So this curve is the one we obtained for individual villa without PV generation. On the other side, we obtained the purple curve for the self-consumer, and we see that the peaks are inverted. So it means that basically like consumer, like people with PV on their roof, like they are exploiting the moment where the PV panel are producing the most, and they are consuming therefore the most. Like this, they optimize their cost. So yeah, I just went through another clustering perspective we tried. So initially, like we tried on metadata, but we also try to cluster directly the time series, so that we can regroup like our client in function of the shape of their curve instead of metadata they have. And what we did was we had some profile at disposal, and we tried to approach basically one which is not super smart, because like we took we computed the daily consumption for each day of the year, and we used them as features. And another approach which was more refined and which should capture the difference in shape of the curve. And we obtain different results, which are kind of interesting, because we can then compare them to the. Basically, we can see which curves belongs to which cluster and link that to the metadata they have. And what we observe are those. So, for example, we see strong seasonality. For example, the red curve and the green curve have inverted seasonality, one with a strong one during winter and another one with strong seasonality during summer. If we look at the metadata, what we've seen is that, for example, for the red curve, which has a strong seasonality during summer, we have, for example, public pools, we have a water pumping station, or we have, for example, campsite. On the other hand, the green curve, we have the ski lift or all the transport cable we are using during winter. And then you see that there are two other curves, the orange one, where basically we are consuming during the weekdays, but nothing during the weekends. So it means that in general it's offices or people in tertiary. And we have this kind of very flat curve or uniform curve, blue curve, which have, and if we look at the metadata behind, what we see that it's apartments or individual house without electrical heating. Another stuff we observe, which can be interesting to generate new tariff, is the following, and also it explains a bit the change of behavior in our clients. So again, if we look, we don't see well the curve, but there is one which is in light gray, which is not the best color, but basically it looks like kind of dromedary, and we have kind of big peak around 7 and nothing around midday. And the one we see here, which looks more like a camel, we have basically two peaks which are kind of similar. So the one at midday and the one at 7 p.m. is the same. And here what we can determine is that maybe now with the increase of home office, maybe the behavior of our customer are changing, because, for example, I'm doing home office. I think I'm consuming more during during midday than during the evening, and this with this kind of observation, maybe we can derive new tariff to motivate our client to consume at different moment in time. And finally, another stuff we can do with this kind of clustering of the curves is that on the first cluster I've shown, like we have a lot of curves inside of it. But if we look at other clusters, some clusters have only one curve. And what we've seen is that it's a really good anomaly detection, because here what we see is that some curve, like their signal have a really high peak, and therefore we have to remove them for further analysis. So basically, the added value of this clustering on time series is that we make the load profile talk. So some information cannot be retrieved from the metadata, but it's also a good check for metadata data quality check, because as I said before, we are using both two kind of data sources. And for example, the heating, it's a bit complicated to analyze if it's correct or not, because like it's coming from open data, and therefore maybe sometimes it says that there is an electrical heating, but in reality it's not the case. As I said, also it's a good, we can also do anomaly detection and identify new consumption behaviors. So my conclusion is the following. So we are just starting to exploit smart meter data. This one is the first project we did, but I think it's kind of cornerstone for further project. We need more data. As I said, some clusters which are maybe more interesting on the third level, like the synthetic load curve, is still of poor quality. And the pressure put on the electric grid and energy supply forces us to be more precise on consumer behavior estimates. And yeah, as I said, a lot of business use case can benefit from these synthetic load profiles. And yeah, it's a good, nice playground for data scientists. And yeah, thank you.
Thank you.